Okay, so just checking that everything works. Yes, my name is Nina. Thank you for coming, and let me thank the organizers for organizing this all for us and for inviting me. It's really great to get together at the end of this tough year, so thank you again. A bit of housekeeping. So we'll have 2 content blocks with exercises at the end of each block, and I'll give you a break. I really encourage you to participate in the talk and to ask questions. So you're welcome to unmute. The keyboard shortcut for unmuting is Alt-A. And if not, you can just write your questions in the chat. Clarifications, questions are especially welcome. We all have different backgrounds. So if you're not following, probably other people are not following either, and I'll be grateful if you ask. I've shared the slides in the chat because this may be useful for exercise sessions. It's kind of hard to fit all the exercises onto one slide, and you can flick back to definitions, you can see the hints, etc.
Could you just re-share the slides just for those who arrived late? They wouldn't have received it.
Yeah, sure. Reshare the slides link. Sure. Let me just do that. I can't find the chat. Can someone just copy paste the link in the chat?
Yeah.
Thanks. Okay, good. So the topic for today is size Ramsey numbers. And the aim is really to give you a flavor of the area, to regain some enthusiasm for research after this tough year, and may possibly get you interested in the open problems. So we're not really building a theory here. And I've decided to go very gentle and only show you one real proof. So in return, you need to fill up the time with your questions and participation. So let's go. The area we're working on is graph Ramsey theory. And the foundational theorem is, of course, by Ramsey. He showed that any red-blue coloring of a large clique, so this is our picture of K of a large clique with a red-blue coloring, contains a monochromatic Kn. So this theorem is about finding a certain organized structure, this monochromatic clique, inside a lot of disorder. And when I say this disorder, I mean we don't have any assumptions on this red-blue coloring. All we know is that the clique is large enough. And this quantitative version is not originally due to Ramsey. He just showed the existence. So this is a later argument. Just to set the scene again, because we all have different backgrounds. So this statement follows the general template of Ramsey theory. So inside enough disorder, you can always find an organized structure. And Ramsey theory is an area of combinatorics that works with such statements. So it includes, for instance, the van der Waerden theorem about arithmetic progressions, and Semiramis theorem also about arithmetic progressions, and several other algebraic and geometric structures. And today we'll be within graph Ramsey theory, where the aim is to find graphs, monochromatic graphs. And a hallmark question in this area is to minimize the size of this large clique. So we want the largest possible, the smallest possible number of vertices that we can put here where the statement is still true. And that's defined as the Ramsey number. This is not a very important definition for this talk. It's just one of the most important questions in all of combinatorics. So bounding the Ramsey number is one of the most important questions. And every bound, every improvement of this bound is a breakthrough. The latest one actually happened this year due to SA. And all of these successive improvements were only just a lower order term in the exponent. So they were able to shave off and something like a logarithmic term here in the exponent. But still, the importance of this problem is not in the tiny improvements, it's in all the ideas and further research that it inspired. So in order to improve this upper bound, these guys had to find better and better methods to embed graphs using quasi-randomness. And I'll return to quasi-randomness later, but in general, disclaimer, everything in this scripty font is kind of vague and undefined. You're not meant to understand it rigorously, just kind of me hand waving. Okay. So faced with this difficult problem and with some early research, Erdős and Boer asked, what about other graphs? So what if we try replacing this structured clique with some smaller graph? Does the question get more manageable? And in general, let's set some jargon. So we usually call this big graph the host graph. So that's the one with the red-blue coloring. And the graph we're looking for is the guest graph. So Erdős and Boer asked about sparse graphs, and indeed they turn out to be easier. So one such theorem is due to Gerencser and Gerfas. They showed...
we have a question.
Yeah.
So I think it's about, in the chat, I think it's a clarification of what exactly is a monochromatic clique.
Yeah, sorry about that. So a monochromatic clique in this is a red clique or a blue clique. So that's actually very important to remember. So I'll try my, my best to draw a simple picture of a monochromatic clique. So inside these, you can always find, say, a monochromatic K4. So this is a red K4 or a blue K4. Okay, please ask if that's still unclear. And let me just then emphasize that, of course, you cannot control which color you get. So the adversary, so an enemy comes and color this graph, and in particular, the enemy can color everything blue. So then you only get a blue clique. Okay, so our next theorem is about finding monochromatic paths. So here it turns out that 3n over 2 vertices actually in the large clique suffice. So an enemy comes and colors the edges of this clique. And by the way, we're always coloring edges. So the enemy comes and colors the edges red and blue. And we can still find always a monochromatic path Pn. And then this was extended to actually all bounded degree graphs. So by that, I mean here, all graphs with maximum degree 10 at most, say. So let me draw again another very bad picture to try and compare this with the previous statement. Okay, good. So on the previous slide, we were looking for a clique of size n, and we needed this huge exponentially sized clique of size 4 to the n to embed that. And now we're looking, for instance, in this Gerencser-Gerfas theorem, we're looking for a path, and it suffices to take a clique of what we say linear sized, and by that I mean linear in n. Okay. So we'll be using this red-blue coloring a lot. So let me encapsulate that in a definition. We say that the host graph is Ramsey for G if any red-blue coloring of the edges of H contains a monochromatic copy of G. So again, a red or a blue copy of G. So this is some notion of robustness. So H very robustly contains G. So even if you let an enemy come and color all the edges red and blue, they still can't destroy all the copies of G. So again, this is an important definition. So in case you have any questions, please let me know. So with that, then this theorem can be restated as follows. You can just say that the complete graph on Cn vertices is Ramsey for G, where G is a bounded degree graph. And now some clarifications on my asymptotic notation, which again, if you work in a very different area, it may confuse you, and you're welcome to ask anytime. So for me, N will be the number of vertices of the guessed graph all the time. I see now there are some questions in the chat. I'll have a look myself. Thanks for asking. No, and I'm about to answer that. So for me, N will always be the number of vertices of the guessed graph. And N will tend to infinity. And then we'll be looking for a host graph of size, say, Cn in this case, where C does not depend on N. Okay, so in this case, C is actually a universal constant. So that's why here, when I say bounded degree graph, I just put a specific bound on it, which is 10, because I don't want to confuse you guys. You can think of C as an absolute constant. For those, again, for those who work more in extreme graph theory, you can actually replace this 10 by any constant delta at the expense of increasing this constant C. But I'm not going to go into that. For us, bounded degree graphs mean graphs of degree at most 10. And I did not emphasize that this, of course, includes a path of length n. So n is our only parameter, and n tends to infinity. And all our bounds will be up to a constant factor. So when I say a bound is best possible, I always mean up to a constant factor. Okay. Again, this notation may be confusing for some people, so you're always welcome to ask, what about the constants in this statement, or how exactly are the quantifiers in this statement? And that makes you look smart on one hand and gives everyone else a bit more time to process. So questions like that are great. So that's the theorem of Hvatal, Rödl, Semeredi, and Trotter. And this theorem minimizes the number of vertices, again, up to a constant factor. You cannot hope to get anything better than n here, because if you want to contain G, of course, you need to have at least n vertices. But you might hope to do better. I see now there was another question before. If we used odd cases instead of 4 to the n, what happens for the graph? I don't quite understand what you mean there. So, yeah, thanks. So you can clarify that if you want. And Thomas, yes, Thomas is one of the people working in this area. So sorry, Thomas, this talk may be very boring for you. You can answer questions in the chat for me instead for me if you want. Anyway, thanks. So, yeah, where were we? Yes, this minimizes the number of vertices in a Ramsey graph for G. But what if we want to go even further? What if we want an even smaller Ramsey graph for G, so something that's not complete? And this was an idea that Erdos, Faudre, Rousseau, and Schelp had. Thomas can also give me a lesson on French pronunciation. And they defined the size Ramsey number as the minimal number of edges in a graph H, which is Ramsey for G. So I'll repeat that. You take all graphs H, which are Ramsey for G, and then you take the minimal number of edges, and that's your size Ramsey number. So this statement implies that the size Ramsey number of your graph is at most quadratic in n, because this complete graph has order of n squared edges. And again, I might occasionally use this big O notation, which just means at most a constant times n squared in this case. And Eros, Fodre, Russo, and Shelp asked for which graphs can you have this linear? So maybe for paths, this Ramsey number can be linear in N, and indeed this was shown by Beck. So Beck wanted to embed monochromatic paths, and he found a graph H with at most 900n edges, which is Ramsey for the path Pn. Now this graph H has really remarkable properties, so let's meditate on that for a second. Firstly, it's really robust against adversarial edge partitioning. So again, an enemy wants to come and destroy all monochromatic paths, and they color all edges red, blue, and they still can't do it, even though this graph is very sparse. And on the other hand, on the contrary, this graph H is as small as possible. So it has a linear number of vertices, but more remarkably, it has a linear number of edges in N. So you can make it bounded degree, meaning that you can make all graphs in this vertex H have degree at most 1,000. And this is again independent on N. So think of N as growing, and yet the degrees in this graph H are still bounded. Okay.
Just a question regarding that robustness. Sorry, is that the same as saying every 4 coloring of the graph has a 4 edge coloring has a long monochromatic path?
Almost. So every 2 coloring. So why did you think it's a 4 coloring?
So just you said like with it being adversarial edge partition, because I thought you did a 2 coloring and then you did a 2 coloring again.
No. Sorry. No, so the way it works is just so edge partitioning is just another way to say coloring, and that's again one piece of jargon that I probably shouldn't use. So really, the enemy gets the graph H, so just the original graph H, and the enemy then gets to color the edges of H red and blue, and their aim is to avoid a monochromatic path. Yeah. And we have another question in the chat. Yes, this factor 900n is not optimal, and there's been a lot of further research optimizing that factor, which I actually won't mention in this talk. So it's very good that the question was there. So let's try and recap those theorems in a concise form. So I'll be using this tabular form to summarize what we saw so far. So I hope that's clear. So in the first column, we have our guessed graph. So far we've seen bounded degree graphs and we've seen the path Pn. Then we see which graph is Ramsey for G. And then the bound on the size Ramsey number that comes from this host graph. So this is just the number of edges in this complete graph, and this is the number of edges in this random graph. So Beck actually showed that the random graph with constant average degree is Ramsey for the path. And here I'm lying slightly for the picky random graphs people. This doesn't have a priori bounded degree, but you can easily clean it up and get a bounded degree graph. That's just a detail. Okay. So the plan for the rest of the talk is to show you the proof of this theorem, or outline the proof of this theorem. It's really classic. And then to look at some recent extensions of the path theorem. So I'll let you stare at that table or stare at this joke, or both. And by the way, regarding emails, so Tim, again, thank you for invitation. He sent a very polite email and he ended it with, by the way, I hope this email is okay. I'm doing this for the first time. And of course, the email was very polite and contained all the info I needed. Anyway, so we'll now go into the proof of this theorem for bounded degree graphs. So I hope this statement is entirely clear. And this theorem uses a textbook tool, the Semeredi regularity lemma, and it's a textbook proof. So I hope that's something you can take away. So let's start with the statement of this regularity lemma. A regularity lemma is all about finding regular pairs in your graph. My Bluetooth headset just died, so let me know if there are sound problems. But anyway, the regularity lemma is all about finding regular pairs. And what are regular pairs? Well, in your graph H, a vertex set UV is epsilon regular if the edges between them look kind of random-like. So this all happens inside a graph G. We're interested in this bipartite graph between U and V. And we want to see a kind of random-like edge distribution, which is expressed in this equation. This is very new to you. Again, don't worry about equations. You just need kind of random-like or homogeneous here. And how do we quantify that? Well, we want that when we take any U prime and V prime in here reasonably large, we want to see roughly the expected number of edges. And what does that mean? Well, this is the edge density in all of UV of the big bear. And we require that the edge density between U prime and V prime roughly matches that. And when I say reasonably large, I mean that U prime and V prime need to have size at least, here should be V prime, sorry. V prime have size at least linear in U and V, so a positive proportion. That means that we can't control small vertex sets. So we can't say anything about single vertices, but we can say something about linear sized sets. And why do I call this random-like? Well, because that's what happens in the random graph. So if you imagine putting edges in here at random with probability, say, 1/2, then between U prime and V prime, you will indeed see typically 1/2 of the edges. This epsilon, again, not something for you to worry about, but this epsilon is a measure of how regular. So the smaller the epsilon, the more regular this pair is. And Semeredi regularity lemma is all about finding regular pairs. So the input of a lemma is a graph H and this parameter epsilon. And the output is a vertex partition such that almost all pairs are regular. So this is the output. So these are the pairs, V1 up to Vm. I should mention here that M is a constant. So what we're thinking here again is the number of vertices of H tends to infinity, but M is an absolute constant. Well, a constant depending on epsilon. And in this picture, these two I drew as irregular pairs. So they're somehow exceptions. We have at most an epsilon proportion of those. And all the other pairs here are regular. And the shade of gray kind of indicates the density. So you know that all these pairs are regular, but they may have density 1, they may have density 0, they may have density 1/2. The regularity lemma outputs this kind of picture for you. And it's a very powerful tool because it applies to all graphs. So suddenly in the last 30, 40 years, half of the proofs in extremal combinatorics start with apply the regularity lemma. In our case, regularity will entirely deal with the red-blue coloring, which again, an enemy comes and does the coloring, so we have no control of that, but the regularity will entirely deal with that for us. And why do we care about these regular pairs? Well, these regular pairs are very useful for embedding. We'll see that at the end of the proof. Okay, so let's go into the proof, unless there are any questions about this statement.
So in this statement of the regularity lemma, so are Vi and Vj, so are I and J distinct?
Yes, yes, they are. So, wait a minute, let me get my pen back. So this may be part VI and this may be part VJ. And yeah, and epsilon, an epsilon proportion of pairs are not regular. And I think to the point, we say nothing inside the parts, if that's your question. So inside the parts, again, we have no control over what happens.
Mm-hmm.
I had a question as well.
Yep.
For a given pair of U and V, is this like epsilon value that, like this level of regularity, is that is monotonic the right word? Are there like
yeah, so again, the smaller the epsilon, the stronger the statement. So you get to, at the start of the proof, you get to set this parameter epsilon. And if you set this epsilon to, I don't know, 10 to the minus 10 in this case, that may be good enough for you, then you will get this constant m depending on your epsilon.
Thanks.
Yeah. Okay, so let's have a look at the proof and see how some of this works. So again, what's the aim? The aim is to find a monochromatic, so red or blue copy of this bounded degree graph G. And again, if it's easier, just think of G as a path for now. So we're given a red-blue coloring of a clique, and our aim is to find G. So we say that we call R the red graph and B the blue graph. And one of them has to contain G. So the first step is, of course, to apply the regularity lemma, say to the graph B. And we get this output, V1 up to Vm. So this may be V1, V2. Of course, my picture is deceptively small. And again, this is an irregular pair. All the other pairs for us are regular. And they're regular, important point, they're regular with respect to both blue and red by complementarity. So we apply the regularity lemma only to blue, but for free, we get that red is also regular in each of these parts. So each of these parts has, again, it's regular in both graphs and has a certain proportion of blue, certain proportion of red. So maybe this pair of parts has a lot of blue and this one has a lot of red, and the purple means kind of something in between. And then, spoiler, our aim is to find parts so that everything between them is regular and has lots of blue or lots of red, whatever we get. But we want to find parts with kind of monochromatic regular stuff between them. So we work inside the so-called cluster graph. A cluster graph is a kind of auxiliary graph that encodes the information from the regularity lemma for us. So here's the cluster graph G. Its vertices are just V1 up to Vm, and it has red-blue edges and non-edges. So this cluster graph C is actually a colored graph. This is a non-edge in the cluster graph because it's irregular. So we entirely ignore irregular pairs. And then this is for instance, a blue pair because it's regular in blue and it has the majority of blue color. So when I say majority, I mean at least a half of the edges are blue. And this also looks kind of blue. And this is, say, blue. And let's say that the remaining edges, they have majority red. So these are regular and they have at least half of red edges. So that's the cluster graph C. And again, it encodes the information given by the regularity lemma. And now we'll kind of mine inside this cluster graph. So first we'll apply Turan's theorem to get rid of the irregular pairs. So the regularity lemma tells you that we have at most an epsilon proportion of irregular pairs. And therefore, Turan's theorem tells us that there is a large clique. In this case, it's these parts. I'll indicate that better, such that everything between them are edges in the cluster graph. So in other words, we kind of get rid of this part using Turan's theorem, and we are left with just red and blue edges.
Could I just ask for what is the statement of Turan's theorem?
Mm-hmm. Yeah, so Turan's theorem tells you, and now I may fail entirely. So Turan's theorem tells you that, I'm just trying to think of notation that we're not using. So F, let's say F is a graph on M vertices. And say that that the number of edges in F is greater than 1 minus 1 over some. Let me do it for this case. No, I'll do it. 1 over A. So it contains, oh, wrong. I'm choose 2. So it contains all edges but this small proportion. Then F contains a clique of size A. And here I think we need strictly larger. And maybe we need plus a little bit. Plus little of 1. And I won't go into the quantifiers there. But basically, Turan's theorem tells you if you contain almost all edges, then you contain a large clique. And this A is a constant. Okay, so that's Turan's theorem. And again, because we get to set this epsilon, so this epsilon for us is in place of 1 over A, so we really get to make it as small as possible. And we find a large clique. And then we apply Ramsey's theorem. Because why? Because we want to pass to a single color. And using Ramsey's theorem, we find a clique of size, blue clique of size 11. In this case, I'll tell you why we care specifically, why we want a clique of size 11. So I will now erase this ink, this Turan's theorem, unless someone objects very quickly. Okay. Now I erased all the ink. So anyway, we apply Ramsey's theorem, and Ramsey's theorem spits out a bunch of parts. Let's see this, so that everything between them is blue in the cluster graph. And now the final step is to actually embed our bounded degree graph inside these parts. So that's step 4. So let me recap what we have again. We have our parts V1 up to V11, and of course my picture only has 3. And the aim and all the property that we know is that all these pairs are regular in the blue graph, and they have at least half of the blue edges. And we want to find a blue copy of the graph G. So again, if you're not familiar with this business, it's enough to just remember that regular pairs make it easier for you to embed. So regular pairs make for algorithmic embedding. But now I'll actually describe how we do the embedding. So the property of the graph G that's useful for us is that the chromatic number of G is at most 11, so that G actually fits within inside those 11 parts. Why is that? Because the degrees in G are at most 10. So that means that you can actually put the vertices of G inside these parts so that all the edges go between the parts. And let me give myself an example graph, a simple example graph here. So let's say we want to embed a graph that looks like this. So we promise that it fits inside the parts V1, V2, V3. And we'll label the vertices here with 1, 2, 3, and 4. And we want to embed these graphs here using regularity. So for the first vertex, V1, it needs to go in here. Notice that we can't choose an arbitrary vertex because we might even have isolated vertices here. So what I'm going to promise you is that V is going to have at least half of the neighbors here and at least half of the neighbors here. And how can we ensure that? Well, using density. So we know that between these two parts, we have at least half of the blue edges, and same thing inside of these blue parts. So indeed, you expect that some of the vertices have at least half of the neighbors here and there, and you can prove that rigorously. So we commit to a specific vertex V1, and its neighborhood becomes a kind of candidate set. So again, this is all informal. It's a candidate set for V2, for the second vertex, and this is a candidate set for the third vertex. Okay, now second step, we're going to embed vertex number 2. And same thing, we need to be slightly careful that we don't mess up the future. So the property we need is because V2 has neighbor 3 and neighbor 4, we need to ensure we don't get stuck there. In particular, this vertex 4, for this vertex 3, will promise that at least half of the candidates set is still good. And for the fourth one, we'll promise that half of the candidate set, like half of this part, is still good. In other words, we're looking for a vertex in here that has at least half of the neighbors in here and at least half of the neighbors in here. And why can we actually find such a vertex? Now we actually apply regularity, the full strength of regularity, because this set where we are fishing, this candidate set has size a half. It takes up a half of the set. So that means that in here we still see roughly half of the edges using epsilon regularity again. And that means that in particular there are vertices that, that satisfy our condition. And same thing in here, so you can actually find a suitable vertex V3. And in this point we are actually done, because now we know we have this candidate set and we can just, oh, this is actually V2, sorry about that, V2. So now we have our candidate set and we can actually embed V3 anywhere here, because we know that all of these are neighbors of both V1 and V2. So here it is. And we can embed V4 anywhere in here. And that gives us our graph G. So I hope that some of that was clear, but the main point is really that we do need these linear sized neighborhoods, So what the property that we really needed was, once we embedded V1, that we look at its neighbors and it's still a positive proportion of the vertices, because then you can kind of inherit the regular pairs. So this neighborhood inherits the regular pairs from the set V3. If this neighborhood was somehow negligible proportion, you would be completely stuck there. You wouldn't totally lose control over the edges. Are there any questions on that proof? Well, proof. Okay, and now,
just regarding the candidate set. So my current understanding is you have like the V1 and the V2, and they're connected to that V3 area, and because they both have size larger than a half, then there'll be something in the overlap, sort of by the pigeonhole principle. So does that mean it has to be quite a fair bit bigger than a half, like a half plus epsilon, the candidate?
No, thanks. And again, that's a very good question. And again, if people weren't quite following the details of that, feel free to just ignore this explanation. But yeah, it's a very good question. So I'll draw it separately. So this is where we actually use regularity. So I'll try and draw the sketch separately. So the argument we are actually using, first of all, let me maybe clarify what Robert meant before I clarify. So this was, I think, Robert's statement, which is too strong for us. He said the neighborhood of V1 is half and the neighborhood of V3 is half. Therefore, they have to overlap by pigeonhole. No, wrong. Half and half plus epsilon, and they have to overlap in this small part. But that's actually too strong for us. So no, that's not the argument. The argument really uses regularity. The argument uses the fact that we have this candidate set for V3, for V2, sorry. So this is the candidate set for V2, and this is the neighborhood of V1. So this is the candidate set for V3. And you're using a regularity between those two subsets. So you're using the fact that, again, by regularity lemma, the number of edges between those two candidate sets, C2, is at least a half. And here it's actually half minus epsilon, but doesn't matter. It's at least a half of the two candidate sets. And therefore, there must be a vertex here which sees at least half of the people there. That's the argument. And then extra level of complication, again, totally not expecting you to follow, extra level of complication. It's not actually enough to have just one vertex there. Strictly speaking, what you need to say is at least, say, 1% of the vertices here have this nice large neighborhood, because then when you look at the third vertex set, you need to overlap again. You need to say at least positive proportion of those vertices are still okay for this set. So really, each time you embed a new vertex in regularity, you're losing a factor of a half in various places. Yeah. Okay. So again, totally, the main point is really just that regularity helps you to embed. And second point, we need linear sized neighborhoods, and we're happy with that. So that's the proof. And let me just then outline draw the basic outline of a regularity proof. So what we did was we started with this red-blue coloring. We applied the regularity lemma to get a cluster graph C. And then inside this cluster graph, we found a blue clique K11, and then we lifted this blue clique into a blue copy of G. And that's a general strategy in regularity. And here we were able to be very crude about the combinatorics. So this K11 is actually a tiny proportion of C, but that's okay because this C had size M, so it's a bounded size graph. So when you take a constant proportion of bounded size, you still have a constant proportion of stuff left. Okay, so that's the proof. Again, way more detailed than expected. And then now we move on to our first exercise session. So we'll be trying to understand this definition of a size Ramsey number and some basic examples. So remember, you take all Ramsey graphs for G and you take a minimal one. I'm not expecting you to do all the exercises, just kind of choose what interests you. So the first exercise is to determine actually the Ramsey number of a star. So this is just a star on n vertices, or with star with n leaves. The second exercise is a lower bound for the double star. So this is a very simple kind of graph that already has a quadratic size Ramsey number. So this is quadratic. Again, this is a star with n leaves here and there. I mean double star. What did I want to say? Yes. In order to prove lower bounds on size Ramsey numbers, what you need to do is consider all potential host graphs and then show that you can color them. So it's, again, tough. Now you need to kill all potential host graphs. So that's the first two exercises. And a third exercise is a very natural fact, but it takes a bit of time to get your head around it. So Erdős, Fordre, Russo, and Sors asked very early on, what if the guessed graph is Kn? Can you get a better size Ramsey number? So can you get a sparse host graph? And the answer is no. So in some sense, a clique is an optimal host graph when you're looking for a monochromatic Kn. And let me spell out exactly how the exercise goes. So you take R to be the Ramsey number, and then you take H to be a graph with a strictly smaller number of edges than the Ramsey graph. And you need to show that H is not Ramsey for Kn. Again, it's worth spending a bit of time thinking about the implications of that. And here I spelled out for you the definition of this R, so you don't have to look up the definition of Ramsey number. So the property you need is that the clique on R-1 vertices has a red-blue coloring, avoiding a monochromatic Kn. Also, Kr doesn't by definition, but that part you don't need. So yeah, don't worry about this. Okay, so those are the exercises. Now it's 4:50, already running a bit, but yeah, we have time. Anyway, those are the exercises. We'll do maybe 5 minutes without hints, and then I'll show you some hints for about 5 minutes, and then I'll solve 1 or 2 of the exercises of your choice. So, the rain is starting. Anyway, I'll get you to just, go away and do the exercises. And again, the slide link is in the chat. So in case you want to look ahead, look at the hints already, you can use the slides. Okay. I'll be here for any questions and see you in 10 minutes. Also, you're welcome to discuss the exercise in the chat. So maybe not out loud to not distract people, but in the chat, collaboration is welcome. Hi again. So I put some hints on the screen there. Don't look at the screen if you want to avoid them. I've also shared the slides again in the chat. And at this point, if you have any questions, you're welcome to unmute and ask them. Hello again. I'll start solving the exercises soon. So can you please, or asking you for solutions. So can you please post in the chat which exercise you would like to see solved? So just 1, 2, 3, which one are you very eager to see? I wasn't able to create a poll, I tried. Okay, it looks like 2 wins, so it's lower bound for this double star. We'll do 2 and we'll I'll show you what the Ramsey graph for E1 is, or someone else will, and then we'll have see if we have time for a bit of 3. Okay. Exercise 2. The double star. Does anyone have an idea?
As a guess, take a tree with depth 2 and a lot of branching out at each layer.
So, what do you mean, take a tree?
So you root a vertex and you have, so you have a star and then you do another layer of star as a Ramsey graph.
But as a Ramsey
Need a lower
graph.
bound.
Yeah. So let me just see that. I think you're thinking of the wrong direction.
Okay.
Let me see that I put down the correct direction. Yes, good. I put down the lower bound. So as I said, for the lower bound, what you need to do, so now you're the enemy. Your aim is to avoid a monochromatic copy of SN. So you need to show that actually any graph with this many edges can be red-blue colored to avoid SN. Okay. But just out of interest, so you said you gave an idea of a graph that is Ramsey for that, right?
Yeah, I was looking on the wrong direction for it. So
Yeah, that's fine. So you were looking at the upper bound, and just out of interest, what was your graph for the upper bound?
So I was mainly working on question 1, but yeah, so for question 2, so
So you mean for question 1 now?
oh, sorry, for question 2 was that double tree.
Yeah, double tree.
Or a
Yeah.
Tree with depth 2.
A tree. This kind of thing was your idea for.
Yeah.
Okay. Yeah, interesting. I'm not gonna try and think about it now, but it could solve the problem. You may need a bit more. I would maybe put a clique here, because what you need is you need all edges between high degree vertices, and it doesn't harm to put a clique here. It's still big O of n squared edges. But anyway, now I'm just digressing. Sorry, let's go back to the exercises. So the exercise is a lower bound, and we need to be able to color any graph. So now, unfortunately, I'm going to have to go to the new screen. So I hope that you have downloaded the slides with exercises. So for E2, we are given a host graph, H, with the number of edges at most n squared over 100. And there I was very crude about the bound. And we need to show that we need to find a coloring with no monochromatic SN. And the hint said, consider the vertices. So I won't write out now what U is, but U is the set of vertices of degree at least n. Why? Because those are the only possible vertices for the two centers, let's say. So let's call these two vertices centers, U and V. And the biggest problem is to embed those two, and that's what we're going to use. So in our graph H, so this is our graph H here, we have the set U of high degree vertices. And can someone suggest a coloring at this point? No. Good. I still have it. Okay, so the coloring is as follows. You color everything inside you blue, and you color everything outside red. Here also everything is red. Okay.
Hi, sorry, I missed this. What defines the set U?
The set U is vertices V, sorry that this is red, versus V in age of degree, and V is the wrong letter, A. The degree of A is at least N.
So
why? Yeah.
So the reasoning here is that if you are going to find a monochromatic copy of the double star, then U and V have to come from the set big U.
Exactly. Exactly. And then it's actually not difficult to finish the proof, because then I'll just repeat that. So if we are to find a monochromatic star, or any star as a matter, the double star inside this graph, then U and V have to live inside this set here. But that means, because all the edges here are blue, that means that Sn has to be blue. But that means that Sn has to live inside this set U, because again, these are the only blue edges that we have. But you can see by counting, I'm not going to do it here, that U is, the size of U is at most something like N over 10 is a safe bound. N over 10, so for sure you're not going to have enough room to embed Sn inside the blue set. And again, the point of this exercise is, well, first of all, to get your head around the definition, and second, that this is a fairly simple graph that already has a quadratic size Ramsey number. Okay, so then we'll do E1, just the Ramsey graph, and move on. So can someone tell me what the host graph age for the star is?
I believe if you just draw the star with the K1 to N minus 1, that should do it.
Exactly. And maybe an argument why that does it, to N minus. Yeah.
Well, as soon as you color the nth edge, it's going to, of a particular color. You're going to have to do that with that final coloring. You can't avoid coloring N edges. And then you
yes, so by pigeonhole principle, there are N edges of the same color, and that will give you a star. Yeah, okay. Good, and again, a third exercise, not gonna do it here, but it's actually a very nice, it's a really beautiful proof. I'll just go back to the statement here, because it's one of the few, because we don't know anything about R, the Ramsey number, or about this coloring that avoids a monochromatic clique, and yet we are able to prove conditional statements on R. And it's a very, very natural questions that Erdős, Fodrer, Russo, and Schelp first asked. Okay. So now I'll jump, and maybe I'll give you a 2-minute break still, just to refocus and to read this amazing comic. So yeah, I'll give you 2 or 3 minute break, and then we'll go back to some extensions of this path result. Okay, so we're back on. And here's our summary so far. Again, our main object of study, the size Ramsey number. And the only fact that we know truly about incomplete host graphs so far is that for the path Pn, we know that we can find a linear sized host graph. And again, this host graph has remarkable properties. And I'll ask you in a minute, how can we possibly extend these results? So maybe be thinking about some other classes of graphs which may have a linear size Ramsey number. And in the meantime, we'll have another story time. I'll give you another more practical reason why we care about sparse, robust graphs. So here's a more practical motivation. We all say in our talks and grant applications that graphs are all around us. But what we don't often notice is that actually typically these graphs are sparse. So when you look at the traffic networks, it's basically a planar graph. In particular, it has a linear number of edges. Same thing with physical networks. So a protein folding network or a crystal lattice in physics is a bounded degree graph, or your brain is also embedded in space. Sometimes edges cost you energy or they cost you money. So that's one property. But a kind of opposite property is that just organically, these networks often end up highly connected, or maybe we want them to be highly connected. And by that, we sometimes mean just small diameter, or maybe resilient against random attack or even enemy attack. So organically, for instance, these social networks and collaboration networks typically have small diameter, which, you know, network scientists call small world networks. So for instance, Facebook, even though it's a fairly sparse network, it has very short average distances. And there's actually kind of an urban myth that you are 6 introductions away from any person on Earth, with maybe few exceptions. On the other hand, if you're engineering a network, you probably want a certain resilience. So if some of the edges fail, you want the network to still fulfill its function. We saw this during COVID. Luckily, the only network that was truly affected was the toilet roll supply network. So that's kind of a vague motivation, but here are some specific research topics that have really flourished in the last 30, 40 years along these lines. So one line is to construct sparse, robust networks. So examples are expander graphs that I'll talk briefly about later, but here's a nice picture to induce your curiosity. Or different models for random graphs like preferential attachment, power law, etc., that kind of attempt to model these social networks. So that's one stream of research. Another stream of research is once you are given a sparse random-like graph, to actually find a certain structure within it, for instance, a long path or a spanning tree. So again, that's difficult because most of our extremal combinatorics classically deals with dense graphs. So we know Turan's theorem, Dirac's theorem, the regularity lemma, they're all about dense graphs. And the recent methods that do deal with sparse graphs are, for instance, sparse regularity and graph limits theory for sparse graphs. So that's our story time. I hope now you really care about sparse, robust networks. And again, our notion of sparseness is, our notion of robustness is that an adversary comes and colors the edges and you want to still see a monochromatic copy of your favorite graph. And we saw that that's possible for a path, that the random graph has this very nice robustness property. And now I have a question for you. So can you guess some other classes of graphs that have this property? And let me break the ice with a silly guess. How about all graphs? So I conjecture that all graphs have a linear size Ramsey number. Can you tell me why that's false? Yeah.
Sorry, can you repeat the question?
Okay, so the main question is, guess some graphs G which may have a linear size Ramsey number. And this is literally just naming your favorite graph classes. And then my conjecture was all graphs. And then Jack is right that, yeah, for instance, the complete graph, it doesn't have a linear size Ramsey number. And we had even the simplest possible example, this double star that has a quadratic size Ramsey number. Okay, so we need the constraint, we need some additional assumptions. What assumptions can we put on this graph G?
Is it safe to say that the number of edges should be sparse in G as well?
So one conjecture is E of G is at most, I'll put a specific constant, say 10n.
So
and
by
again,
the results earlier, we had the bounded degree also?
Yeah, that's true. Okay, so we say this is false. Again, a counterexample is the double star. But, so let's assume bounded degree. So everything we consider now, because of this double star, we'll assume that everything we'll consider will have bounded degree. So what are some suggestions within the bounded degree world?
Cycles.
Yeah. How would you generalize a path, maybe naturally?
Grids.
Yeah, that's a very interesting example. So grid, that's this kind of graph.
Trees?
Double star though for tree is an issue.
Yeah, but we're
degree.
living in a bounded degree world. Yeah.
Okay.
Yeah. Okay, so yeah, we have some suggestions now, and let's see what's actually true. I did not list, there's one natural conjecture actually that no one said, is that all bounded degree graphs, so all graphs of degree at most 10 have a linear size Ramsey number. That's a natural conjecture asked by Beck, but surprisingly, Rödl and Semeredi proved that it's actually false. And maybe the fact is not that surprising itself, but the proof really is because, again, you're the adversary, you want to kill a copy of G, so you need to know how to color every single host graph. So in light of that, we have two kind of main streams of research. One is, if we still insist on the linear size Ramsey number, what additional assumptions can we make? And those are, we had some suggestions there, trees, cycles, grids, planar graphs, etc. And another suggestion is, well, let's try and live with bounded degree. Can we still get something subquadratic? That's kind of what, again, Jack suggested in the chat. And we had this quadratic bound that we kind of proved. Can we still get at least a little bit better than that? And that's actually true, and that's a big result of sparse regularity. So that came out in the annals, even though it's a fairly small looking improvement, and because it really advanced our knowledge of, again, sparse regularity and how to embed things in random graphs. And then for linear size Ramsey numbers, we had some additional classes of graphs, which I probably won't go into in detail now. But let me at least talk about bounded degree trees. So Friedman and Pippinger showed that bounded degree trees have a linear size Ramsey number. So again, here bounded degree, I mean degree at most 10. So for instance, binary trees. And this is a very important paper because they actually, their host graph is a so-called expander. And expanders are these very rare and very powerful classes of graphs that appear all over computer science and number theory. And recently we had many more constructions of expanders. So again, the Friedman and Pippinger techniques, they're really important because they're algorithmic techniques to embed inside expanders that have been widely used afterwards. So now I will do, almost skip to the exercises. Let me just give you a table kind of comparing most of that. So I've skipped over these results. So let's see what we saw so far. I've kind of color-coded them according to techniques. So we have these two theorems that embed inside expanders. And then we have this theorem that embeds inside a random graph that's just kind of medium density, let's say. And then we have the intermediate results that embed things inside blow-ups of expanders. So you take an expander, you blow it up. And the reason that's significant, so one reason that these results are significant is that they are able to deal with large cliques inside your guessed graph. So before that, we didn't know quite how to deal with cliques, how to embed cliques. And these two results go around that issue. So I'm sorry that this was a bit fast, but then the first kind of natural open question is indeed the grid. So as Robert suggested, a grid is one graph that doesn't belong quite in here. And it's a natural bridge towards planar graphs. So what I'd really like to see is actually that bounded degree planar graphs have a linear size Ramsey number. But for now, anyway, let's stick with cliques. And this group already showed that using the random graph, you can attain n to the 3 halves. And that's the best possible thing you can hope for with a random host graph. So you need to come up with an innovative kind of host graph if you're hoping to beat this bound. But it's a very nice problem. And I believe Thomas knows more about this proof, so he could present it for us.
Yep.
So that would be it about the results. And then here are the open questions that I want to get you interested in. Again, that's the grid. This is improving on the results for bounded degree graphs, again, potentially difficult. And these are two interesting results for hypergraphs. I will just mention this one, the first one. The first one is extending the path results to hypergraphs. That's something that's not known and very natural. And it's actually known for uniformity 3. And they use these kind of blow-up-y techniques. Okay, so that was a quick scroll through the open problems. And then we'll have 10 minutes for our last exercise session. So here are the exercises, or alternatively, you can use that to think about the results that I just said and some of the questions. So here are the exercises. Maybe I would focus on, I'll just annotate and choose a subset. So I would focus on these two exercises about random graphs, if that's your thing. Kind of exploring how much you could possibly get from a random host graph. Or this is a kind of Friedman-Pippinger type result that tells you that if you have a certain weak kind of expansion properties that you can embed long paths. Okay. So you're welcome.
PN2?
PN2 is this blow up of a path. Yeah, I didn't explain that. Yeah. Yeah, it's you take a path and you replace each vertex by 2 vertices and you add all the kind of natural edges between them. Yeah. So yeah, I'll give you, say, 7 minutes, and then we'll briefly discuss the exercises. Okay, so the hints are on, and again, I think if you want to do 7, you would probably find a hint useful.
Is question 5 a question about size Ramsey or regular Ramsey?
Who is that? Just so I know who I'm talking to.
It's Tim.
Hi. It's a question about the density version of size Ramsey. So you may know that Semiratis theorem is a density version of van der Waerden, meaning that you allow you allow an adversary to come and remove, say, 90% of your integers, and you still contain an arithmetic progression. So that's kind of the kind of statement that you often ask about Ramsey results. Can you, instead of having red-blue coloring, can you say that even 10% of your graph has the desired structure? And indeed, this is what Friedman and Pipperger showed, that if you take an expander and you leave only 10% of the edges, and you still contain any tree. But this exercise is kind of says that it's wishful thinking for most other graphs.
I see, yep.
I'm back. So can you please post in the chat which exercises you're dying to see solved? Okay, so Jack just broke our tie. Thanks, Jack. Okay, so let's try exercise 7. So let's read the hint first. So again, what does this exercise say first? Let's say, so the assumption is about our graph H that any two sets U and W of this size have an edge between them. And notice that this is quite a weak assumption actually, because these sets are huge. I mean, what this assumption is saying in the contrapositive, so we'll actually prove the contrapositive, is that if H does not contain Pn, so if H does not contain Pn, then you can find huge sets U and W. So they comprise almost the entire vertex set with nothing in between. So that's kind of the opposite of expansion. It's the opposite of quasi-randomness. Okay, so that's, again, some certain weak property implies that you already contain a Pn. And how do we prove that? Well, the algorithm says the solution says we start with this algorithm. So we run this algorithm. So we want to build a long path. We start with a single vertex and then empty set W, and everything else is in U. And we try to extend this in each step. Our aim is to extend the path using vertices from U. So we're going to seek edges in this set U. Once we are successful, so let's say we found an edge here, then this vertex, say X, will move to the path. So this is X, and we'll remove X from here. So X gets deleted. And then we repeat the same property. So we keep extending the path. Let's say that now we find that X is actually a dead end, so we don't see any vertices here. Then we add X to W. So now X gets removed. That's the algorithm. So I'll draw this once again. So at every point of the algorithm, we have this path P. We have a set U, which is a set that we haven't explored, the set of vertices to explore. And we have a set W, which is kind of the set of dead ends. And the important thing is, again, once we are unsuccessful in this, so let's say this is a vertex V and we are unsuccessful, then this vertex V moves from P to W. So what are the important properties of this algorithm? I'll say one property. One is that throughout the algorithm, so these sets U and W are changing throughout the algorithm, so that's a bit unrigorous of me. But anyway, at every step, there are no edges between U and W, because again, W is the set of dead ends. You've only inserted vertices that you know have no neighbors in U. And the other property is something about sizes of U and W. So can someone tell me what kind of property we need about U and W?
Is it that W is bounded by that condition we had at the start? So like if W ever gets big enough, then there will be a connection with the other set? Is that?
I think that depends on your assumptions.
Okay.
So here's, no, I mean, what I'm going to say is that depends on whether you're proving, and I wasn't clear there, whether you're proving the contrapositive or the original statement.
Yeah.
And I think you're right. You're trying to prove the original statement. And at some point, when W becomes too big, then you will say, look, there are no edges between U and W contradiction.
Yeah.
Okay. But I will explain the contrapositive version. So sorry about that. Our assumption is that Pn is not contained in H. So then the condition, say star, implies that at every point in time, U plus W is at least V of G minus N. And that's by star because throughout the algorithm, this path we are building has length at most N. Okay. And then at some point during the algorithm, because what we're doing is we're emptying U and we're increasing W throughout the algorithm. So we start with W empty and we keep filling it up, filling it up. At some point they will cross, these sizes will kind of cross. So at some point we'll have the property that U equals W. So at some point we'll find these two sets which have no edges between them because of property large, 1, and they're large because of property 2. So again, the point is expansion, very weak sense of expansion implies long paths. Okay, I don't think we have time for other exercises. I'll just write here, because people were interested, that the answer is NP to the 10th. So that thing gets positive when P is at least this amount. And okay, I will say, okay, sorry, I'm for running over. One more important thing is that this density is a bottleneck for greedy embedding, precisely because it has this nice, the graph, at this density you get this nice property that any 10 vertices have a common neighbor, lots of them actually. And below that density, you no longer have that property, so the embedding gets much more difficult. Okay, that's that from me. Some literature, again, if you download the slides, and thank you for listening.
Yeah, thank you, Nina. Let's give a big applause to Nina by unmuting ourselves. Yeah, it's a very engaging talk. I really like it, thanks. So yeah, thank you, all of you, for attending